Here they're telling us that we have some galvanic cells, and they want us to make a sketch, which you can do in any format you like. You don't need to turn it in. But they want us to give the coefficients in front of each of the different species in the overall equation. One thing to note, it's important, in galvanic cells, the cell potential must be positive. And that tells us which of the half reactions to flip around. So if we look at table 18.1, you'll see some of these species in each of the half reactions. We have iodate ion, an iodine molecule, and some water. Well, the only half reaction that we see that includes all of those is this half reaction. With a voltage of 1.2. And then the other half reaction involves iron 2 and iron 3 ions. Well, the half reaction that involves those ions looks like this, with an associated voltage of 0.77. Because it's a galvanic cell, we have to pick the half reaction to flip so that when the voltage is flipped and added to the other voltage, you still get a positive result. That means we will flip the half reaction that involves iron ions. So let's rewrite that one, flipped around. Iron 2 becoming iron 3 and an electron. The voltage then flips to a negative 0.77, and to clear this up, I'm just going to erase this middle line here. So now we've got two half reactions. We're going to add them together. We have to make sure that the number of electrons crosses out. We've got 5 electrons in the reduction half reaction and only 1 in the oxidation half reaction. So we're going to multiply by 5 all of the coefficients in the oxidation half reaction. Note, that does not affect the voltage for that half reaction. Voltage is a ratio. So crossing out the electrons and adding together, we get an overall equation that looks like this. And if you want, you can include the voltage, overall voltage of 0.43. Now there is one little problem. WebAssign asked to give the lowest possible coefficients. Well, one of the coefficients in our overall equation is 1/2. That's technically not possible. You can't have half of a molecule. So to make this the lowest possible coefficients, we've got to double everything. So instead of 1/2, multiply everything by 2, and we have 2 iodate and 12 hydrogen and 10 iron 2 ions and a full 1 iodine molecule. That does not affect the voltage. It remains 0.43. Okay, so what can we write in the answer blanks? 2 for iodate, a 10 for iron 2, a 12 for hydrogen, a 10 for iron 3, a 1 for iodine, and then a 6 for water. In terms of a sketch, I would suggest something that shows at least an anode and a cathode, and whether you want to draw something with a porous disc or a salt bridge, I don't care, as long as you're indicating ion exchange in some way. We've got to have a stick of metal in there. And since we know that the reduction half reaction was the one that had iodate ion, and the oxidation half reaction was the one that had iron 2 ion, and neither of those half reactions includes a solid species. We've got to put platinum. Platinum is the non-reactive metal that you need just as a material to serve electrons and receive electrons. Okay, let's, it doesn't matter which side you put the cathode on, let's just put it as the left side. Cathode, of course, is where reduction occurs, and the anode is where oxidation occurs. And you need to include everything that's on the reactant side of the overall equation that's aqueous. So, for instance, from the reduction half reaction, we have iodate, we have hydrogen, and if you wanted to, you could include iodine. It is not necessary, it's optional to include that. I'll put it in parentheses just to indicate that. In the oxidation half reaction, we have iron 2 ion. So at a minimum, you've got to have iron 2 ion. You may also include, it wouldn't hurt, you could put iron 3 ion. Not necessary, but welcome and encouraged. Okay, they also want us to show direction of electron flow. Since Leo the lion says grr, and losing electrons is oxidation, the chamber that is associated with oxidation is losing the electrons. Electrons always flow from the anode to the cathode. So whichever side you drew the anode on, the arrow should be pointing away from that side. And that roughly completes our... Oh, and if you wanted to, just as a nice touch, the overall voltage, 0.43. Okay. Problem B. They're giving us some clues as to which half reactions we're dealing with. Zinc neutral becoming zinc 2+. Silver ion becoming neutral silver. Okay, checking out a table of standard reduction potentials. We see these two half reactions written. No, that's flipped around, excuse me. Start that part again. From the table of standard reduction potentials, the zinc reaction looks like this. The silver reaction looks like this, with an associated voltage of 0.8. One of those two has to be flipped around, so that when you change the sign of the voltage and add it to the other voltage, you still get a positive result. In this case, we'll need to flip around the zinc reaction. After flipping the zinc reaction around, so that it becomes an oxidation half reaction, we get something that looks like this. We'll have to double the coefficients in the silver reaction so that the number of electrons crosses out when you add the two half reactions together. But that does not affect the voltage. Total voltage is a positive 1.56. And if we look at the problem up above, and they want us to fill in the boxes, we have a coefficient of 1 on the left side in front of neutral zinc, a 2 on the left side in front of silver ion, a 1 on the right side in front of zinc ion, and a 2 on the right side in front of neutral silver. And the last part is to draw a sketch. The sketch doesn't have to be super detailed, and it doesn't certainly have to be very good artistically, but it does have to show just basic info. So for instance, I'm labeling the porous disc because I realize my artistic talents may be limited. I'm showing a stick of metal in each chamber, and just for kicks, I'm going to put the cathode on the left side and the anode on the right side. You could have flipped that and it's no big deal. Cathode, of course, is the place where the reduction reaction occurs, and the anode is the place where the oxidation half reaction occurs. Since we flipped the zinc reaction, the oxidation reaction is the one that includes zinc, and we kept the silver reaction, so that's the oxidation half reaction. So the zinc reaction, which includes, which is the oxidation half reaction, would have a neutral solid, and that would be zinc, and floating around in solution we have zinc ion. In the reduction half reaction, we've got neutral silver, that's the metal, and we have silver ion floating around in solution. We have to indicate the direction of electron flow, and as we mentioned before, Leo says grr. Losing electrons, which is the oxidation chamber, means the electrons flow away from the oxidation chamber. So wherever you drew the anode, either left side or right side, make sure the electrons are flowing away from it. And gaining electrons is reduction. The reduction chamber is receiving the electrons. And then one last nice touch, not required, but if you wanted to include the overall voltage, you could.